Hi everyone. This video is the solution to example 1 on the topic of flexibility method. Before we solve this problem, we are going to first look into the theory of flexibility method. The first thing we need to understand here is that we have 4 different reactions. In this case, we have the vertical reaction at A, horizontal at A, also a moment at A, and then we have a vertical reaction at C that we're going to call VC. Flexibility method is a method to solve indeterminate structures. This is an indeterminate structure to 1 degree. And why do we say it's 1 degree? Because if we count the amount of reactions, the amount of unknowns, we have 4 of them. And to solve this type of structures, we only have 3 equilibrium equations. So the problem here is that we have 1 more reaction than equilibrium equations that we can use. That means we need to figure out another way. In this case, we need to figure out another equation that in the context of the flexibility method, we're going to call them a compatibility equation. So what's the idea of the flexibility method? We have this structure that we don't know how to calculate. So in this case, has the load of 72 and then fixed support on the left and then a roller support on the right. And we can say that this could be the load of 72 without the support plus having another structure that doesn't have the load of 72 but has the reaction VC. We know how to calculate these two structures. And what we're interested in calculating is the vertical displacement at C from structure 1 and also calculate the vertical displacement at C from structure 2. So if we call this our structure number 1 on the left and this one on the right, number 2, and we're able to calculate these two displacements, what we can then say is, and this goes back into this idea of compatibility equation, is to say we calculated structure number 1 and structure number 2. Neither one of them has a support at C, but the support at C exists. And that support, what it does is that the vertical displacement at C has to be equal to 0. This is what we call, in this context, the compatibility equation. And now what's the idea of the compatibility equation? If we understand that this original structure we have on the left that we're interested in calculating is nothing more than structure number 1 plus structure number 2, our vertical displacement at C will be nothing more than the 1 from structure 1 plus the 1 from structure 2. And then we know this has to be equal to 0. Our unknown is VC. So this compatibility equation helps us calculate the reaction of the support we removed. But okay, after this theory, let's now try to solve this problem. So if we think about this in terms of steps, our first step is to remove a reaction. And then our second step is to calculate the displacement due to the loads. So if we want to calculate the displacement due to the loads in the position where the support is to be, this is our real structure. And we can use unit load method, so we can use a virtual structure that has a load of 1 in the direction of the displacement that we try to calculate. And again, remember, we're trying to figure out this vertical displacement at C for structure 1. To do this, what we have to do is get the bending moment diagram for these two structures. And if we check the sizes of the structure, that's 2 meters and 2 meters. So this is 2 meters, this is 2 meters. So we know this bending moment is going to be like this. So 0 where the load is applied and then maximum at the support. And this is going to be equal to 144. And we also know the other bending moment diagram will have a maximum of 4 because now the distance from the load is 4 meters. So we know this is the bending moments that we have. Now, due to the unit load principle, we can calculate the vertical displacement at C for structure 1, which is nothing more than multiplying this triangle with this trapezoid here. Now, if we want to define this trapezoid, we need to find this value here in the middle, which should be equal to 2. And we also know the base here is 2 meters and the base there is 2 meters. So if we want to know this vertical displacement, we're going to do triangle times trapezoid and divide by EI. So we're going to get 1 over EI. And now if we check the table of integrals, this should be 1 over 6 and then A plus 2B. This is the dimensions of the trapezoid times C times L. So in this case, what we're going to get is 1 over EI times 1 over 6, and then A and B are the dimensions of the trapezoid. So that will be 2 plus 2 times 4 times 144 and now times 2. And this should give us a displacement of 480 divided by EI, which in this case, if we think about it, the displacement has to be down, which makes sense because this is positive and the unit load we're assuming is 1 kilonewton down as well. So this displacement is downwards. So far so good. We calculated the displacement due to the loads. Our next step is to calculate the displacement due to the reaction. So now, what's the problem with calculating the displacement due to the reaction? Is that we actually don't know the reaction, so we can't calculate the displacement. So what we're going to do instead is, instead of calculating the displacement due to this reaction, Vc, we're going to calculate the displacement due to a load of 1 kilonewton. So if we place the 1 here, we're still interested in calculating the vertical displacement at C, but now in structure number 2. One thing that is worth to notice here is that this case is actually very similar to the one that we just used for structure number 1, but instead of putting the load down, we are now putting the load up. So to save us a little bit of hassle and to calculate another bending moment diagram, what we're actually going to do is to flip this and make the load of 1 kilonewton down and then measure what is the displacement caused also down. In this case, both the real structure and the virtual structure are exactly the same as the virtual from the previous example. So what we're going to end up doing is multiplying this diagram here, the diagram from the second structure, times itself. So what we're going to do is the displacement at C due to structure 2 is nothing more than a triangle times a triangle divided by EI. Triangle times a triangle is 1 over EI, and then 1/3 ACL. So what we're going to get is 1 over EI times 1/3. And now if we check the diagram, the values of A and C is 4, and the span is also 4. What we get in this case is 64 over 3 EI. If you look at the structure here, you can see that the displacement has to have the same direction of the load. So what have we done so far? We removed the support reaction, we calculated the displacement due to the loads, and we figured out is 480 divided by EI, and we also calculated that for a load of 1, the displacement is 64 over 3 EI. So now, our final step is to write our compatibility equation. That's nothing more than to say the vertical displacement at C has to be 0. This is what the support offers, the support that we had from the beginning. We removed the support, but now we're going to put back the effect that that support gives me on the structure. That gives me an equivalent structure that then I know how to calculate. But now, what is this vertical displacement at C? Is nothing more than the 1 from structure 1 plus the 1 from structure 2. And there's something missing here, but for now, let's just say equal to 0. So now let's substitute and say the vertical displacement at structure 1 is 480 divided by EI, and the one from structure 2 is 64 over 3 EI equals to 0. What is missing is the vertical reaction at C. If we go back into the beginning, we discussed that we're interested in finding the vertical displacement on structure 2 because on structure 2 we applied the load Vc. But that's not what we've done now. What we've done was apply a load of 1. So what we figured out was the effect of applying a load of 1 has in this structure. And because we are assuming linear elastic behavior, we can scale this solution Vc times until we get the compatibility equation solved. What we're basically saying here is that our original structure that looks like this is nothing more than the one without the support and the load of 72 plus another structure with a load of 1 at the tip, but at the end we need to multiply by Vc, so then we can calculate the value of Vc in this case. And that's basically it. So now if we take this equation here and try to solve it, we know that the EIs will simplify and Vc will be equal to 480 divided by minus 64 over 3. And what we get in this case is minus 22.5 kilonewtons. And now, what does this minus come from? What is the meaning of this minus? This minus just means that wherever we apply the load of 1, if you guys notice, we are applying the load of 1 always downwards, here, here, and here. We just figured out that This minus sign tells me that my reaction is upwards. It's the opposite of what I'm assuming since the beginning of the problem. This is how you solve a structure using the flexibility method. So if you go back into the beginning, our idea is we remove a support, we start calculating displacements as if the support is not there due to the loads. Then we calculate the displacement for a load of 1 in the position of VC. So let's write here again for a load of 1. And at the end, we write the compatibility equation that states that the vertical displacement has to be 0 because we have a support there. With that equation, we find the reaction VC, so that's the reaction we chose to find since the beginning. And now our problem is solved because now we now have 4 reactions and 3 equilibrium equations, but one of the reactions is solved. So that means now we can find the other 3 using methods that you learned in the previous years. So using equilibrium equations, for example. So before we close the video, our final step is to calculate the final bending moment diagram. Now, in this case, we could solve the bending moment diagram in a very simple way, just by saying that we have a load of 72 kilonewton, but now we know that VC is equal to 22.5. And now we have a statically determinate structure. We could get the reactions, we could get shear forces, and we could calculate the bending moment straight away using this method. But this is not the easiest method to use in this case. Because if you guys remember that we are saying that our structure, and I'm going to try to draw it, is nothing more than our structure with a 72 plus VC, we can times this by our second structure with a load of 1. So if we now take this equation, we can say that our final bending moment diagram is nothing more than the bending moment diagram we got from the loads that we have already. It was with 144 plus VC, and now we can multiply this by the diagram that we got for the other case. And the last thing we need to do is replace VC with the actual value of VC, which was minus 22.5. Our final bending moment diagram will basically look like this. On the right supports, if we look at the right, here is 0, there is 0 as well. So we know our moment here is 0, which has to be. If we look at the left support, our moment here at the support will be 144 minus 22.5 times 4. So I'm taking the value of this moment over here, and I'm subtracting the one that is here in the second structure times the value of VC. If I do it like this, I can check that this moment will be equal to 54. Finally, if we're interested in finding the moment in the middle, for example, we know that it's the value on this diagram, so this one is 0, plus the value on this one, that's 2, times minus 22.5. So this one here is going to be 0 minus 22.5 times 2, because 2 is the value of this diagram over there. So this gives me 45. So now I'm in a position to draw my bending moment diagram and conclude the problem. I just want to first talk about this minus 45 here. What this minus basically saying is that it's the opposite moment as the one you see here. Here we have a negative moment, so we have tension on the top. And if we have a minus sign, that means at this point we're actually going to get tension on the bottom. So we're going to get a positive moment. And this is it. This concludes this problem, and this is the first example of flexibility method. Thank you for watching, and have a nice day.